Should I start?
Yep. Go ahead.
Okay. So I'm John Baily. I'm a professor at the University of Colorado in Boulder. What I work on primarily is to study the way stars and planetary systems form. And the first thing I'm going to tell you is that you guys, especially you guys, live in a remarkable time. You are part of the first generation in the history of this planet that has access to the entire electromagnetic spectrum. So up until about the 1860s or so, all astronomy was done with the eye alone. And if you want to record a picture, you have to make a drawing, a painting, a sketch. Then we invented photography. It was applied to astronomy 1890s. And photography was the primary tool of astronomy until about the 1960s or so. Up until then, all astronomy was essentially in this narrow sliver of the spectrum that we can see with our eyes or can be detected with film. By the 1920s, we opened up a new sliver called the radio window, and you guys here have a radio telescope, and you can see a little bit of what radio astronomy can deliver. But the real revolution started about the 1960s for two reasons. First, we gained access to space. Why was that important? Because the Earth's atmosphere blocks virtually all the colors, all the wavelengths of light that come to us from the distant universe. We can only see the visual wavelengths our eyes can see, and the radio waves, which radio telescopes could see. So access to space was crucial, but also the rise of our silicon technology, the ability to fabricate sensors that work from gamma rays to X-rays to ultraviolet to infrared. But that technology really is only started to mature in the 1990s. So you're literally part of the first generation of access to the spectrum. And more remarkably, in the last few years, we've opened up new spectra. A few years back, we detected for the first time the signal of a pair of black holes merging via the gravitational waves, which cause ripples in space-time to propagate at the speed of light. So we've opened up a new spectrum of gravity waves, and somewhat analogous to light, to electromagnetic waves. I'm not going to talk about that. I'm going to talk about something much more familiar to us. In fact, you can see it with your own eye, namely the constellation of Orion. Why do I speak about Orion? Because I'm primarily interested in seeing how stars and planetary systems form. And it turns out that Orion contains one of the nearest regions where young stars are forming today. And this multi-wavelength ability to see the sky is absolutely revolutionizing what we now know about star formation and how planetary systems form. So let me start with an introduction to Orion. This is the constellation as seen by the naked eye. There it is. The bright star Betelgeuse is a supergiant, a red supergiant. It's actually at the end of its 10 million year life. And Rigel down here, also a blue supergiant, also approaching the end of its life. Something you have to know about stars. Sun-like stars live for something like 10 billion years. They live by consuming hydrogen, converting it to helium, and that produces the energy which makes the sun glow. Massive stars, ones which are 10 to 100 times as massive as the sun, consume their fuel between 1,000 to up to 1,000,000 times faster than the sun consumes its fuel. So even though those stars have a lot more fuel, their lifetimes are much shorter than that of the sun. So the massive stars like Betelgeuse and Rigel will die within tens of millions of years of birth. By the way, the solar system took well over 100 million years to assemble. So while some stars are still assembling their planetary systems and forming, others are dying in their immediate vicinity. We can see these processes in Orion, as you will see. Let me zoom in a little further. This is Orion as it's setting. There's Betelgeuse, Rigel, the three belt stars which make the constellation visible. And if you look carefully, notice that one of the stars down here, it's not a star, it's called the Orion Nebula, is actually fuzzy. It's a cloud of hydrogen gas lit up by the light of some stars that are extremely young. In fact, we think that the central four stars, the trapezium stars, that you can see through the eyepiece of the telescopes tonight, are only something like 100,000 years old. They just emerged from their birth clouds tens of thousands of years ago. And that region, as you will see, is surrounded by thousands of forming low-mass stars that we can study today. All right. If you take a slightly different, this is a little badly colored, but this is the view of the entire visual winter Milky Way. There's the winter Milky Way. There's Orion, Betelgeuse, Rigel, the three belt stars, the nebula I pointed out. You notice that in this picture, there's a lot of red light. There's this arc of gas that you can see. It's something like 20 times the size of the full moon. You can't see this easily with the naked eye because it's so dim. But a time exposure, this is about a 1 minute exposure with a Canon 60DA, if you know that kind of camera, shows you this feature quite nicely. By the way, there's the Pleiades star cluster of stars that formed about 100 million years ago. Back here is the Hyades star cluster with the star Aldebaran, the constellation of Taurus. That cluster is almost 1 billion years old. So you can see in the sky stars of various ages. And of course, here's the Milky Way. So I'm going to change your view, give you a sense of what it means to be able to see other wavelengths. This is a view of the same winter sky. This is visual, and it's registered to an infrared view. So I've retuned your brain and eye to a wavelength that's about 100 times, 200 times longer than what your eye can actually see. This is taken with an infrared satellite in orbit called the IRAS satellite at a wavelength of 100 micrometers, which is about 200 times the length of the light that your eyes can see. And you notice that the sky is full of clouds, not stars. In fact, there's very few stars. The only star you can see here is Betelgeuse, that one. Whoops. Oop, there it is. It looks blue in this picture. It's a red supergiant star. It's surrounded by a dusty envelope which reprocesses its light into the infrared, so it glows at these long wavelengths. But most of the stars you see in the visual wavelength view have disappeared because they don't emit as much light in the infrared as at visual. Their light has been, in fact, reprocessed, absorbed by interstellar clouds of dust, which gives you this reddish glow. Here's the Milky Way. And here in the constellation of Orion, just below Betelgeuse, you see two concentrations of bright dust clouds. In fact, over the last few decades, we've learned that there are two massive clouds in Orion. Each weighs about 100,000 times the mass of the sun. And those stars, those clouds, are condensing under the force of gravitation. They're fragmenting and producing hundreds and thousands of young stars in the process of fragmentation and collapse. So that's what we're going to be talking about today. So I'm going to come back to this visual picture again because I'm going to point out something somewhat odd. We've learned from satellites that make precision measurements of the positions and distances of stars that every so often stars are ejected from their birth sites at very high speeds. For example, in the 1950s, an astronomer by the name of Adrian Blau compared photographs taken 50 years before his time with photographs taken in the 1950s and realized that two 10th magnitude stars, one in Auriga and one down here in the constellation of Columba, are flying out with a speed of about 100 kilometers per second. If you trace back their motions, they came from very close to the Orion Nebula, about 30 arc minutes south, half a degree south of the Orion Nebula. Those stars were ejected by some process about 2.6 million years ago with an uncertainty of about 50,000 years. So what's the process that can eject some stars? Well, we'll talk about that. But I'm going to tell you today is that one of the recent results on our studies of the Orion Nebula is that such an event, an ejection of two massive stars, in fact 3 massive stars, happened in a very recent past. The light from that event would have reached Earth about 550 years ago. Now that's not when the event happened because Orion, the Orion Nebula region, is about 1,300 light years away from us. The event actually happened in AD 175 plus or minus 25 years. That's when I think Marcus Aurelius was emperor of Rome. What happened, we think, as you will see, is that 2 or 3 stars interacted, 2 of which collided, merged into a more massive star, and in that process released more energy in the course of a decade or so than the sun puts out in 10 million years. It was a cataclysmic explosion in Orion, and I'm going to show you how we learned about this event in the next 30 minutes or so. By the way, if you take this visual wavelength image and subtract all of the stars, you can do this by taking narrowband images in the light of hydrogen, and then taking another narrowband image just off at a different wavelength, which does not contain the light of hydrogen, and you subtract the two images, you can see what the distribution of glowing hydrogen gas in Orion looks like. This is the same scene registered. There's Betelgeuse. Whoops, going the wrong way here. There's Betelgeuse. There is optically. There's this loop that you see in the red in the visual wavelength picture. When you subtract the stars, it's much more prominent. There's the Orion Nebula. You notice that the entire constellation of Orion is filled with glowing, dim hydrogen gas. And in fact, there's a giant bubble that's been inflated by massive stars in Orion that were born over the course of the last few to tens of millions of years. So there's a lot of energetic processes happening in Orion. Now I'm going to zoom in a little bit closer. There's again Betelgeuse, Rigel, the three belt stars, the Orion Nebula. There's this arc. I'm going to show you a somewhat better picture of this in a minute. But I'm going to retune your eyes again. This is visual wavelengths, and registered to this, I'm going to show you what the European Planck satellite, which measures gas and dust at wavelengths of order a millimeter, show you what that patch of the sky looks like. So here again you see this loop. I'm going to actually magnify this scene in a second. You'll see this loop in red, and you'll see there's two giant clouds in Orion in green. Here's the Barnard's Loop, as it's called. Here's the Orion Nebula in the foreground. And here's one of the giant clouds in Orion. Here's the other one. Each of these clouds has a mass of something like 100,000 times the mass of the sun. Many years ago, actually about 20 years ago, we mapped this patch of the sky in New Jersey with an antenna at the AT&T Bell Laboratories using a tracer called carbon monoxide, a simple organic molecule. It turns out that these clouds of interstellar gas are mostly made of hydrogen, a little bit of helium, and then some of the heavier elements like carbon and oxygen combine to form simple molecules. The simplest ones of those is carbon monoxide. And this is a picture of what the distribution of carbon monoxide in Orion looks like. And you might ask, what's the color? Well, because we're using a radio telescope, we can measure the motion of the molecules of carbon monoxide with a precision of about 100 meters per second away from us or towards us. It's the same technology that a policeman uses when he catches you speeding on a highway. If you're approaching the policeman's radar, you can measure, your speed can be measured. Similarly, if we see a carbon monoxide molecule approaching us with a few kilometers per second speed, the frequency and wavelength of the light is shifted in such a way that we can determine the motion with a precision of order meters per second, even though the source is located 1,300 light years away. So red in this picture corresponds to gas moving away from us at something like 10 kilometers per second with respect to our standard reference frame. Blue is more or less stationary, and green is in between. And you notice there's kind of a systematic trend of red, green, and blue here. And then this is more confusing here. By the way, the Orion Nebula is not visible in this scene, but you'll see how it fits into the picture in a minute. If you go to even longer wavelengths, 1.1 millimeter, and look for compact dust cores, we can now see the clumps of dust which are in the process of forming stars. So there's a satellite called the WISE, Wide Field Infrared Survey Experiment, which mapped Orion. And these yellow dots that you see in here are not stars. They are clumps of gas and dust which are emitting in the infrared, which are in a process of condensing to form stars. In fact, you notice that up here, there's this blister or bubble, that is itself the Orion Nebula. That picture I'm outlining here is about twice the size of the full moon. That is the Orion Nebula you can see through the eyepiece in the telescope upstairs tonight, seen at infrared wavelengths. And then on one corner you see this really bright, intense spot. Turns out there's a massive core which is producing massive stars today. And it was in that core that 550 years ago, there was a powerful explosion triggered by the merger of two stars, which set off a very violent event. Okay. By the way, how do we know the distance? There's a phenomenon called parallax. Because the Earth orbits the sun, our vantage point toward Orion changes during the course of the year. If you have a precision telescope that can measure tiny positional differences in the positions of stars with respect to more background stars, we can measure the so-called parallax oval. As the Earth orbits the sun, nearby stars describe a small oval with respect to more distant stars. It's the same effect as if you cover, you have two eyes in your head. So if I hold up my finger and I cover up one eye, my finger is to the right. If I view that finger from my other eye, it shifts to the left. That same effect can be used to measure distances of stars. And right now, there's a satellite in space called Gaia, launched by the Europeans in 2013, which is measuring the distances and motions of about 1 billion stars in our Milky Way throughout the galaxy. And this satellite has now told us the details of how far various parts of Orion are from us. In fact, this is a cartoon which illustrates the same cloud I showed you before in the previous slide, where the Orion Nebula is, up here in the upper part of Orion. And this is now showing the distance in units called parsecs. A parsec is roughly 3 light years. So 400 parsecs is roughly 1,200 or 1,300 light years. And so the Orion Nebula, which is up at the end up here, is about 390 parsecs away from us. And the cloud, which is in the sky, goes to the south, is progressively further and further and further. So we now know, for the first time in the last few years, something about the three-dimensional distance to various parts of Orion. It's quite remarkable. This again is Orion, seen in carbon monoxide, the red gas moving away from us, blue gas approaching. I'm going to zoom into this box. This shows you dust. It's a very thin filament. In fact, this hot, bright region is where massive stars are forming in Orion today and where that explosion took place. So I'm going to zoom into that. Before I do, I'm going to show you some of the more detailed view. Here again is Betelgeuse, Rigel, the 3 belt stars. You notice now in this deeper picture, you see this loop of red gas, hydrogen gas. You see the Orion Nebula down here in what we call the sword region. The cloud that we saw before extends down here and up here. There's a famous cloud here called the Horsehead Nebula. If you're an amateur with a big telescope, you have a really dark site up in the mountains, and there's no moon, you might be able to glimpse with a low-power eyepiece the Horsehead Nebula. It's a little silhouette of a dusty cloud against the bright hydrogen gas that's glowing here. You can see the nubbin of the Horsehead poking out there in detail. By the way, this structure, this blue cloud, is scattering the light from Rigel. And because of its shape, it's been called the Witch Head Nebula. I guess it looks like a witch, like the veils of a witch. By the way, what Gaia and the previous astrometry satellite called Hipparchus has told us is that Rigel and Betelgeuse and 2 of the belt stars are actually in front of the bulk of Orion, about half the distance to Orion. In fact, one of the mysteries we're trying to understand is what is this foreground population that contains Rigel and Betelgeuse? They didn't form in the main clouds of Orion. They just happened to be superposed in the foreground. Okay. So this is now zooming in. We're going to zoom into this very central part where the Orion Nebula sits. This is an exposure in a near-infrared. This is the classic visually detected shape of the Orion Nebula. You can now begin to see some of the thousands of young stars that form. By the way, around the sun, the nearest star, Alpha Centauri, is about 4 light years away. In a box that's 4 light years across in Orion, that region will contain something like 2,000 or 3,000 stars. In the core of the Orion Nebula, the nearest stars are only some like 3 or 4 times further than Pluto is from us. So if you lived in the center of the Orion Nebula, you look around the sky, you would not know about the rest of the universe because you'd be blinded by the light of thousands of stars, some of which are massive and luminous, up to 100,000 times as luminous as the sun. And they light up this glowing hydrogen cloud. It'd be like living in perpetual twilight of the Orion Nebula. You wouldn't be able to see distant galaxies or distant parts of the Milky Way. Yes?
Would it be really, 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 really hot?
Well, that depends on what you mean by hot. So I can tell you that in the core of the nebula, the gas is 10,000 degrees. However, it's very tenuous. So if you're an astronaut, you would actually radiate heat more efficiently than the hot gas around you would heat you up. And actually you would find that you would, despite the 10,000 degree plasma surrounding you, it's so tenuous that your ordinary radiation would cool you to only tens of degrees above absolute zero. You'd freeze to death in a 10,000 degree bath. How do we know this? It's from our infrared observations. Because we see dust particles floating in Orion. We can measure the temperatures. Those dust particles are just like the astronaut's body floating around in Orion. The dust has a temperature of about 50 degrees, above absolute zero. You'd freeze to death. So you wouldn't want to go there. Anyway, this is Orion infrared. I'm going to retune your eyes again to the millimeter waves, carbon monoxide. And so I'm going to use images from this telescope called the California Array for Millimeter Astronomy. The millimeter doesn't refer to the fact it's a very small telescope. It refers to the fact that the telescope sees light with a wavelength of 1 millimeter. And by the way, at millimeter waves, the sky's always black, except for water when it's cloudy. But if it's day or night, doesn't matter. As long as the sky is clear, it's transparent. You can do daytime astronomy at radio wavelengths because the sky is completely transparent. So we took this array of telescopes and combining the signals from each, we synthesize a telescope that's up to 1 kilometer in diameter to make an image with a resolution that's much better in your naked eye of carbon monoxide in Orion. So here's the result. Here's this picture of Orion in infrared, and I'm going to show you what the carbon monoxide looks like, but it's a data cube. This is not just a picture. This is a data cube, and I need virtual reality to really show you the data, but I don't have that. So I'm going to show you color pictures, which shows you different slices of this cube in color. Here it is. Here's the first one. We call the project Karma Orion. The acronym Karma, this sounds good, it's karma, good karma, is the name of the array. And of course, it's Orion. And we use the isotope 12 carbon. We can see several isotopes of carbon monoxide, no problem. By the way, the numbers here represent the way the gas is moving away from us. 5 kilometers per second, 7 in blue, 7 in green, and 9 in red. Looks complicated, doesn't it? And this is a data cube. So let me just show you what a cube looks like. I'm going to go through it. There it is, there it is. So holy cow, what's going on here? Well, notice something. See this dust that's obscuring this part of the nebula? If you go back to this picture, you can see it glowing in carbon monoxide. Look at this blue edge. I'm going to go back a little bit here. I'm going to come back into the green channel. When I go all the way back to the cube, notice that corresponds to this reddish, dusty edge of the Orion Nebula. You're seeing dust that's been pushed up and heated by that 10,000 degree plasma, tenuous plasma, in the core of Orion. Okay. So what's this about an explosion, you say? By the way, this is the Hubble Space Telescope view of the core of Orion. A little overexposed. There's 4 stars. In fact, if you go up to the eyepiece, up here, you can see those 4 stars easily. Those are the so-called trapezium stars. This particular star, that one, called Theta 1 Orionis C, you don't have to remember that, is 40 times as massive as our sun. It's emitting light 100,000 times more furiously. It's 100,000 times as luminous as our sun. By the way, every one of these stars is multiple. The most recent studies with adaptive optics have shown that amongst those 4 stars, which you can't see in this picture, is that each one is multiple. There are 15 stars altogether. This one is a sextuple. That one is a triple. This one's a triple. That's a double. Every one of these massive stars is multiple. That's the rule amongst massive stars. Almost all are in multiple systems. And what you can't see here is the thousands of low-mass, sun-like stars, because the massive stars are so much brighter, and the glow of gas is so bright. Okay, how do stars form? So I'm going to take you through a video animating 250,000 years in the life of a cloud that's spherical, has about 50 times the mass of the sun, undergoing gravitational collapse. Self-gravity causes the gas to condense, to get denser and denser. By the way, this is the elapsed time. We've now just seen 197,000 years. 197,000 years in the life of this cloud. You'll see star-like objects called sync particles emerge in the simulation. And where you see one, you get many. Gravity causes the stars to interact like a game of billiards, chaotically. They interact, they eject each other, forming a small cluster. And this is a cartoon. It does not capture all the physics. I won't go into the details of that physics. But we now know from observations that as young stars form, they're surrounded by disks, spinning disks, which are magnetized. Magnetized disks launch jets of high-velocity plasma, which feed back energy momentum and limits the fraction of gas that can go into stars. It's a self-limiting, chaotic process. It's dynamic. And we now can observe this dynamicism with satellites like Gaia. We can actually measure the motions of stars and learn how they're moving about in a forming young cluster. I mentioned jets. Here's an example of an isolated young star. There's a cloud. In green is the hydrogen alpha edge. In blue is oxygen. In red is an ion of sulfur. And if I retune your eyes to this scene, you say, where's the star? There's no star there in the middle. Go to the infrared. Wow, there's a star. It's a double star. And you can see it's blown a bubble. This is registered, by the way. You can see the background stars are the same. But the view is infrared, about 10 to 20 times the wavelength of visual light, and visual light. And now if I go over to the Hubble Space Telescope and look at this part of the system, this little filament, here's what it looks like. I should skip that. Here's that filament. This is taken way back in 1994. We came back 3 years later with Hubble. You see it move? Things change in the sky. And that motion corresponds to, when you take the distance into account, about 300 kilometers per second. You get from here to LA in 2 seconds. A young forming star surrounded by a spinning disk entraps magnetic fields. Magnetic fields build up energy until it's like an aneurysm. It erupts, launching a jet at high speeds. All right, skip that. By the way, jets are all over. This is a part of Orion. In this picture, there's a jet there. There's a little cluster of jets here. I'm going to zoom into this field right here. There's a jet, there's a jet, there's a jet. You show me one star forming, and I will show you dozens or hundreds. Stars are gregarious. They form in clusters. Everywhere. Almost all stars form in clusters. And they eject each other. And the field population of the Milky Way is produced by those ejections. The sun itself, we think, was born in a cluster with thousands of other sibling stars, including massive ones. In fact, the reason we are here is because the Earth inherited short-lived radioactive species and long-lived radioactive species. We still today heat the core of the Earth, make the Earth an active planet with geology. Stop geology. Stop the radioactive heating, your planet freezes. No more recycling. You end up looking like Mars. No atmosphere and dead and dry. By the way, that's what a jet looks like when you look at it in the infrared. Like a lightsaber from Star Wars.
How long?
So this is about 1/10 of a light year. So it's a lightsaber. It's a light year long. Here's my message. I'm going to show you the evidence for this. The explosion in Orion happened in about 175 plus or minus 25 years. That's our uncertainty. Released more energy than the sun puts out in 10 million years. What's the evidence? Well, we went to this facility in 2013. It's called the Gemini South Telescope. And it illuminates a constellation of artificial guide stars, 5 of them, 5 sodium lasers shot into the upper stratosphere. And this allows us to correct the turbulence in the Earth's atmosphere to a level which is better than the Hubble Space Telescope. With this 8-meter diameter telescope, we got images twice as sharp as the Hubble can take. Of course, not at visual wavelengths. We did this in the infrared at 2 microns. By the way, that's what Gemini looks like. There's the laser beams going up into the sky. There's a 5-point constellation of artificial stars. And what we saw is this. Those 4 stars are the ones we talked about before, the 4 massive stars that light up the Orion Nebula. 1/10 of a light year behind those stars, in a core that's hidden from visual wavelengths, but is blazing bright at millimeter wavelengths, a small cluster of massive stars formed over the last 100,000 years. And they produced this thing, which looks like a 4th of July fireworks display. Let me show you this in more detail. I'm going to scroll up from the bottom of the screen. In blue, you're seeing iron vapor heated to thousands of degrees by shock waves. In the orange, you're seeing shock waves of hydrogen produced by ejecta flying out at up to 400 kilometers per second. It's an explosion. Okay? So with this data, we went to the Atacama Large Millimeter Array. So the world's most ambitious ground-based telescope today is in Chile at an altitude of 15,500 feet. Why? Because the Atacama Desert is dry. And at that altitude, there's much less water vapor above the site. So an international consortium of the United States, Canada, East Asia, and Europe spent about $1.6 billion to build the most ambitious ground-based telescope ever built, called the Atacama Large Millimeter Array. This instrument is like the Hubble Space Telescope from the ground. Its resolution now, by combining the light from 64 separate telescopes spread over 14 kilometers of altiplano desert in Chile, can synthesize an image with a resolution that's 10 times sharper than the best images produced by Hubble. And it senses the cold universe. It is designed to look back over cosmic time, over the last 14 billion year history of cosmic evolution, to trace the formation of galaxies and stars from the very beginning of star formation about 400 million years after the Big Bang. That's what ALMA is designed to do. But that's not what I want to use it for. I want to have it look at Orion. And so here's what ALMA... Well, actually, before I show you that, let me show you that this is an explosion. This is an image taken in 1999. And we went back in 2013 with adaptive optics. Got this image. Note, oops, wait a minute. That's my computer. That's the cosmic microwave background. What happened? How did that? Hang on. Okay, that's telling me whether that's working. Maybe you shut it off. Maybe that's what happened.
The laser works out. It's on. It should. Can you plug the USB thing back in?
Yes. The HDMI port. It's back in, right? The purple cable.
The antenna.
Maybe is the antenna back in? Can you tell? Well, and let me tell you what you're seeing here. So if we can get this thing. If you can, yeah, go ahead and try to. But the button doesn't seem to be responding. That's what's very strange. So I can't advance or go backwards with the thing connected. Strange. That's a new one. By the way, this is the ALMA image with 1 arcsecond resolution. You're seeing in blue gas that's approaching me 0 and minus 100 kilometers per second. And in red, gas that's receding at roughly 20 to 120. You're seeing an explosion in the carbon monoxide gas. It's about 10 times as much gas here as shown as the mass of the sun. I've also marked the positions of 3 stars, which I want to show you in the other images, because these 3 stars are moving. This guy, called BN, otherwise known as the Becklen-Neugebauer object, and its claim to fame is at Mount Wilson, where your 24-inch telescope came from. Eric Becklen and Jerry Neugebauer used the first infrared detector at 2 microns in the 1960s, a detector gotten from the military, called a tank buster. It's basically the device that was designed to look for engine heat so it could target missiles. That was used by Jerry Neugebauer and Tom Seufer to look at the infrared sky. They detected the first star that does not have a visual wavelength counterpart in Orion, called the Becklen-Neugebauer object today. It's a 10 solar mass star, and with radio observations we learned, oh fantastic, there it is. That guy's moving up that way, speed of about, go backwards. You can't go backwards? Okay, what on earth? Now let me tell you a story here, and then we'll stop, because we'll have to reboot the computer, I think. BN is moving this way at about 26 kilometers per second. There's a massive star, and in fact my ex-student Adam Ginsberg and I measured its mass just last year with ALMA data. Using the 0.04 arcsecond resolution of ALMA, we found, first of all, there's a disk, contains about a couple of tenths of the mass of the sun, orbiting that star. And by measuring the way the gas particles are orbiting in that disk, we could use Kepler's laws to measure the mass of the star. It's a 15 solar mass star. Now here's the weird part of that story. When we published our paper, we measured the disk spinning motions using a line of water vapor, which originates about 2,000 degrees above the ground state. 2 other lines also gave us the rotation, and we did not know what was to carry those emission lines. It was a mystery line called an unidentified spectral line. Then a chemist in Charlottesville, Virginia, this summer, identified one of our lines as, you won't believe this, salt. Interstellar salt. Potassium chloride. We used that information. We found that the second line was sodium chloride. We went back to our spectra. We found something like 30 emission lines of salt vapor in Orion. We just published that paper. It was a press release last Wednesday from the National Radio Astronomy Observatory reporting our discovery of interstellar salt. A dash. That's source I. Interesting, last year, in fact 2017, Kevin Luhman used Hubble Space Telescope to find that there's a third star that was ejected. This one is called Source X, from an infrared catalog from the 1990s. It's not visible visually. That guy's trucking 55 kilometers per second. Approximately 550 years ago, when the light got here, all 3 stars where that X is located. Notice that all these fingers originate from very close to the position of that X. What happened where the X is? We think essentially in the 100 or 200 solar mass dense cloud core, which forms several massive stars, the stars are orbiting. But the orbits are through a viscous, gaseous medium. There's gas, there's drag. The orbits shrink. The stars get closer and closer together. And 550 years ago, or actually at 1,300 light-year light travel time, AD 175, 3 stars interacted within less than 1 astronomical unit of each other. And these young stars are bloated. They have a size of order an astronomical unit, which is the Earth's separation from the sun. The stars, as a result, collided. The cores merged, setting off a powerful explosion. that emitted more energy than the sun puts out in 10 million years. That's what set off this explosion, and that's what we think happened in Orion. All right, let me stop there, and we'll see if we can reboot the computer. And I can show you the motions of the stars and also the motions in the gas from about 20 years of data. Oh, did you get it back?
Yeah, I can change it for you. What do you want?
Oh, go back. Okay, perfect. Thank you. So I'm going to show you. By the way, there's a source eye disk, scene edge on. Go back. Back. Go back. Keep going. Keep going. One more. There's Alma. One more. Now, we're going to blink this. Go back one more. Two more. One more. Okay, now, I want you to blink. Image taken in 1999 with the Subaru telescope in Mauna Kea. Next picture. 2013. Go back and forth. See, the stars don't move, the gas does. That's the motions, and the motions are about 200 to 400 kilometers per second. Now, let's go back ahead 2 frames, not back. There's Beckman-Nogabar object. Look at this star. Blink. Let's see. Go ahead. Go forward. Back. Not that far. 1999. 2000. Did you see that star move? That's what 55 kilometers per second at Orion looks like. Okay, next. Want to see what 15,500 feet at night looks like in the Atacama Desert? That's Alma. By the way, that's the valley floor, 15,500. That mountain, Cerro Sajnantor, 18,000 feet. Nice place to go. Yes? So that's the Milky Way. So this is a wide-angle lens. And the reason the Milky Way is not straight, the reason it's bent, is because the wide-angle lens distorts the appearance of the sky when you project it onto a flat screen. That's a very good question. Thank you. Okay, next slide. That's what the explosion looks like superposed on a near-infrared image. Here's the trapezium stars. There's the debris flying out. By the way, the debris is not yet visible optically, except in 2 small locations we actually see with Hubble knots of gas emerging from the background cloud. In something like a few hundred years, your great-great-great-grandchildren, when they look in Orion, will start to see dozens of these fingertips starting to emerge, producing shock waves at visual wavelengths in the nebula as the explosion emerges. Next. There's that view again of Orion. Here's the current source in the infrared, source X, BN, and the radio source I is still not visible, even though it's a 10,000, 20,000 solar luminosity star. 15 times the mass of the sun. It's so embedded, we have to go to radio wavelengths to see it. Next slide. There's the explosion. I'm going to zoom in. Now we're going to go to the VLA in New Mexico, the Very Large Array. That's near Socorro. Here you can see the radio emission from the Beckman-Nogabar object, source I. Source X is not visible. This glow is the 10,000 Kelvin dilute plasma of the Orion Nebula. That's in the foreground. Next slide. This is the infrared image. There's Beckman-Nogabar object. There's source X again. Next slide. This is ALMA, looking at the same field. That's the source I. Notice it's elongated. It does not look like a star. Next slide. I zoom in. By the way, this is VLA, just a point source. The VLA does not have the resolution of ALMA. That's registered. Go back and forth, blink between those 2 things. Yeah, so there's source N. You can see that. Point source there at ALMA. Radio jet with the VLA. Next slide. Here's how we're going to measure the curve. Here, this disk is spinning. We're going to look at the Doppler shift of 2,000 Kelvin water vapor in the next slide. There it is. This is kind of a physicist's diagram. This is position. This is velocity, speed of orbital motion. 20 kilometers per second approaching 0, 20 kilometers per second receding and so forth. You see this S-shaped curve. That's how we measure the mass of the star using laws of gravity. All right, next slide. Now, click on this, and this is an animation of what we think happened. Just put the mouse in there. Cursor. There's a hand. There should be a hand that you can put in there. You use the...
Working on it.
Okay. A little hand that you kick on, push it, it'll turn on the animation.
I don't think it's
Not going to collaborate? Okay. All right, skip it.
You can kind of, why don't you just dance it?
All right, everyone get up and start buzzing around. Yay! That's a kind of a cartoon of what we think happened. All right, next slide. I think we're at the end here, finally. So here's my conclusions. Stars form from the gravitational condensation and fragmentation of dense interstellar clouds. By the way, these clouds don't only contain molecules of hydrogen, a little bit of helium and carbon monoxide. They're a witch's brew of organic compounds. We've detected compounds like ethanol, methanol, ethyl cyanide, methyl cyanide, heavy organics, polycyclic aromatic hydrocarbons. Interstellar clouds, when they produce stars, dump a witch's brew of heavy organics onto those forming stars. Now, most of those molecules break apart in the heat of star formation. But planets, which form around those stars, inherit a witch's brew of heavy organic compounds. It's no wonder that life as we know it is carbon-based, because we inherit a rich carbon chemistry from interstellar space. When we look at young stars, we see they produce jets. And in cases like Orion, explosions. And I think Orion's not unique. I think, in fact, many massive star-forming regions in the sky exhibit this kind of behavior. Interactions between stars leading to mergers and collisions and explosions. And that's a mechanism which self-regulates the fraction of gas that can be converted into stars. A typical cloud like Orion, by the time you've converted a few percent of the mass of the gas into stars, the star formation process has produced so much energy that you blow apart the cloud. You've stopped the star formation process. It's only in extreme environments, leads to the birth of globular clusters, where the feedback is overwhelmed by gravity. When you stop the feedback, when you throttle it back because there's so much gravity that nothing can stop the collapse, that's when you convert 90% of the mass into an enormous cluster like globular clusters like M13, converting maybe the entire 100,000 solar masses of a cloud into stars. That's how you get the bound clusters like M13. Okay, we're almost done. Here's the bottom line. Interactions among stars and the resulting ejections probably are a fundamental aspect of what determines the masses and properties of stars. And I'll stop there. I apologize for all the computer glitches. Sorry? What was that? Okay.
Error is human to release.
To err is human, indeed. Yes?
Some number of years back, they synchronized telescopes, radio telescopes on the opposite sides of the Earth.
Yes.
Now, wouldn't that have more resolution?
Yes, the problem is that you can only sense really bright sources. So, yes, aperture synthesis, in fact, intercontinental interferometry, as it's called, can synthesize micro-arcsecond resolution. In fact, right now the best tool is a Russian telescope called Radio Astron. It flies in a Molniya orbit, an eccentric orbit, out to 10 Earth radii. Unfortunately, the politics prevents the United States from collaborating with that project. The Germans, the Europeans, the Chinese are scraping up all the science. So we are getting 10 micro-arcsecond resolution with that, but it only works for what's called non-thermal sources that are intrinsically super bright, the so-called masers. Mother Nature's laser emission at microwave wavelengths. That's what radioastron can really measure. And by the way, we've measured parallaxes using those masers. Has lots of interesting results. We can measure the masses of black holes in nearby galaxies using that technique.
So this is all for your next book.
Perhaps. Yes?
How did that event in Orion compare with a supernova, and did it pose any threat to the Earth?
Excellent question. So first of all, the energy of Orion is only 0.1% of that of a supernova. The explosion will kind of peter out by the time it reaches a radius of a couple of tenths of a light year. So there'll be a few more thousand years, but it's so far away, 1,300 light years, not going to touch us. Now the question you might want to ask is, what about supernovae? I mean, they're much more powerful. So can that damage Earth? Historically, there's no evidence that in a 4.5 billion year history of the planet, we've actually been severely impacted by supernovae. But there's been minor impacts. For example, the oceanographers will, when they dig down into deep ocean sediments, they find over the last 10 million years that we've been impacted by radioactive species from 4 nearby supernovae. There's radioactive iron-60 in deep ocean sediments, which we think comes from nearby supernovae in a so-called Scorpius-Centaurus association of nearby massive stars. That's about 300 light years away from us. So the debris has actually been captured by the Earth. Microscopic amounts, parts per 10 to the 12th in the ocean sediments. But it's enough to know that we've been impacted in minor ways by nearby supernovae in recent times.
So when Betelgeuse blows, we should know that as well too, right?
It'll be spectacular, but it's too far away. Yeah. It'll blow another 50,000 years. I'm not a betting person, but if I were to bet which star is going to blow next, Eta Carinae on the south is most likely.
Is there a pool among the stars in terms of...
No. Not to my knowledge.
Star Deadpool, as it were.
Yeah. Yes.
When the 3 stars merged, why did they explode?
So what happens is a release of gravitational potential energy, we think. So actually, 4 stars interacted, 2 of them merged, and the other 2 stars were kicked out, and the merger remnant itself was kicked out. Okay? Now, there's a possibility that there may be a nuclear component to this event as well, because massive stars reach what's called the main sequence hydrogen burning stage really fast. So these stars probably already had cores which had more or less are burning hydrogen via something called the carbon-nitrogen-oxygen catalytic cycle. Turns out that cycle has an incredibly steep temperature sensitivity. Temperature to the 16th power, which means I increase the temperature by 1%. The burning rate increases by 16% to first order. So it's possible that the dynamics of the interaction perturb the core of those merging stars enough so that you actually set off a nuclear flare as well. That could have contributed excess energy beyond what's released by gravitational potential. So that's just a hypothesis. We don't know that for sure. And I'm not a modeler, and I need someone who's an expert in 3-dimensional modeling of stellar structure with nuclear physics. That's a highly specialized skill. I don't have that. So, yes?
Is it possible that another star can explode?
So stars, well, if they get hit by another star, yes. But typically explosions of stars only happen for isolated stars for the most massive stars. So we know that stars more massive than about 8 times the mass of our sun all will essentially explode as supernovae, releasing about 1,000 times as much energy as the Orion event released. Stars less massive than that don't explode, but they swell up and shed most of their mass rather gently back into space. Their cores then settle down to something we call a white dwarf star. Imagine a star, mass of the sun, but whose size is that of the Earth. Now, by the way, the massive stars, the ones that explode, sometimes they leave behind something called a neutron star or a black hole. A neutron star is a star about the size of Berthoud, maybe 10 kilometers across, that contains as much mass as the sun. Your thumb would contain as much mass as the Empire State Building in New York. About a cubic kilometer's worth of rock would fit into your thumb. That's the density of a neutron star. A really massive star, even neutron star doesn't form, it forms a black hole. What's a black hole? It's an object so dense that the escape speed is the speed of light. So not even light can escape. That's why it's called black. Light can't escape. Looks dark. Good question. Thank you. Yes?
The stars that were ejected from that event, and it seems like sounds like it's rather common, right? If any of those stars have planets, did they have those planets before they got ejected, or did that happen afterwards?
So that's an interesting question. There's a certain radius. So if we accelerate a star to, say, 10 kilometers per second, any part of a pre-existing planetary system or gaseous disk whose orbital speed is larger than 10 kilometers per second, which implies that those particles or planets are orbiting closer to the parent star, they'll be dragged along. In fact, we think that the disk around source I that we measured to determine the stellar mass was actually dragged along. So the disk pre-existed the event, and then as the star was ejected, the outer disk was blown away, but the inner part of the disk, the stuff that's orbiting close to the star, was dragged along. So that's what the thing happens. It's what we can talk about the details later. So yeah. Any other questions? Yes.
Where did all the carbon monoxide come from?
Well, so hydrogen is the most abundant element in the cosmos. Helium is number 2, about 30% by mass, 10% by number. Oxygen is number 3, 1 part in 10 to the 4th of hydrogen around in the Milky Way. Carbon is about a factor 2 less abundant. So carbon and oxygen combined, they make the most abundant molecule next to hydrogen. Now, there's a complex chemistry. So the hydrogen can react with the carbon and the oxygen to make hydroxyl and CH. And then other hydrogens come in. You can make methane, ammonia, with the nitrogen that's present. And that starts a whole complex chemistry. And so all the carbon goes down a chain of ever more complex chemical reactions until you get polycyclic aromatic hydrocarbons with dozens of carbons and nitrogens and hydrogen. Where did it come from ultimately? Supernovae. The universe, as far as we can tell, the Big Bang produced only hydrogen and helium, nothing else. In fact, when the nucleosynthesis of the early universe was worked out in 1948, it was considered to be a great failure because it could not understand the abundances of the elements. And then various people like Fowler, Burbidge, and the 2 Burbidges worked out that in massive stars, you can convert hydrogen to helium, helium to carbon, helium plus carbon makes oxygen, and you start working up the periodic table. And when the supernova happens, all that material that was synthesized in the core of the massive star, up to iron, gets blown out to space, mixed with the hydrogen, and voila, here we are in a second generation star. Okay? Now, where does the heavy elements come from, heavier than iron? And we just learned the answer to that 2 years ago. Things like gold come from neutron star mergers. We just detected in August 17th, 2017, with the LIGO gravitational wave array, the merger of 2 neutron stars. We saw a chirping signal over 200 seconds. Started out at something like 20 hertz. That's the orbital motion of the 2 stars. Imagine, 2 neutron stars orbiting each other 20 times a second. The emission of gravity waves caused the orbit to shrink over a course of the next 200 seconds. By the time the event happened, the stars were orbiting each other 400 times a second. The 2 neutron stars merged, set off what's called a kilonova. And in that process, the spectra show heavy, rare earth elements were synthesized. That's where we think the heavier elements in iron mostly come from. Neutron star mergers in compact binaries. Merging of stars happens all over the sky. By the way, that event happened 300 million parsecs away from us. And we detected the gravitational waves from that thing. Yeah. Okay. That's it.